Yeah, it's okay. So this is the paper, right? Yeah. So this is the paper that we are going to discuss. It's the 8th paper, but maybe I don't know how many you guys have written. It's the 8th paper. So let's discuss this. Okay. So let me now just go to the whiteboard and yeah, share. So let me not discuss the first question because we kind of discussed that yesterday. I will discuss it in the end if needs it. Second question, I have seen that you people have partially done. So should we do the second question? Let's see. Let's begin with the third question. Yeah, because the third question, it seems like no one has done. Yeah. It's in fact easy. It's just, I think, interpretation of matrix multiplication. So let me just say the question. So yeah, it was slightly incomplete. Yeah, but nobody asked me for the clarification. So Raghav asked me, I had replied to him. But anyways, yeah, let me state it. So this is a mock 8 and let's see problem 3 because this question kind of no one, yeah, maybe because it's incomplete. So there are 4 vertices. So let's just draw the graph. Yeah. So there is 1, 2, 3, 4. There are 4 vertices and then there are some arrows. Okay, so there's an arrow from 1 to 2. There is an arrow from 1 to 2. There is an arrow from 2 to 3. And there is an arrow from 3 to 4. So this was the incomplete portion, but either you could have made an interpretation and tried or asked me, yeah, 3 to 4. And then, but yeah, and then there is an arrow from 1 to 4. So that part is clear. So, I mean, you could have taken arrow from anything to 4. The answer would not matter because of a certain thing, because the 1, 4 is there. Okay. Note one thing, very important thing, that you are not getting a cycle. Okay. That we are not getting a cycle. So let me go back to the question paper. Now I've lost it. Yeah. Okay. So you're not getting a cycle. Now, a point is that we are going to make a matrix out of this graph. Okay. Are there any other edges? No. Okay. There is another one from 1 to 3. Okay. Well, let's just do one thing. Okay. Let's not put that edge right now. Okay. There is an edge 1 to 3, but let's solve a simpler version. This version you guys can do on your own later. And then we are making a matrix. Okay. And this is a matrix and it's like indexed by the rows. I mean, sorry, it's the rows and the columns are indexed by the vertices. So 1, 2, 3, and 4. And at the ijth vertex, we are just recording if there is an edge from I to j or not. That's all, right? So like, yeah, so 1, 1 obviously is 0. Yeah. And similarly, you can see 2, 2, 3, 3, 4, 4. These are all 0. Okay. And 1, 2 is 1, 2, 3 is 1. Okay. 3, 4 is 1. Okay. And then there is 4, 1 to 4. So that will be 1 in the here. Here we will have 1. Okay. And okay. So 1 to 3 is also, let's actually just put it. Okay. So 1 to 3, there is this thing. And so that will go in here. Okay. Everything else is 0. So what else am I missing? So this one is 0. Everything else is 0. You see? Okay. So this is what you can see. This is the matrix. All right. Now, by some college algebra formula, the answer can be given. But by some very simple combinatorial interpretation, the answer can be given. What is the question? So if this is the matrix A, okay, we want to show some power of A is 0. So first, you guys should tell me some attempts that you should have made or you can think of now. Okay, no idea. Okay, fine. So if like a natural thing to do is to try to calculate A square. Okay, I mean that maybe is one thing. Okay, But let's say you don't want to just compute a square. Let's say you want to understand the interpretation. So let's say that in a square, I ask you, let's say I pick the, let's say 1 to 4, this one. Okay, this entry. Okay, so I mean, how do you get this entry? How do you get this entry in a square? Yeah, you will have to take this thing, right? And you have to multiply it with this thing, the last column, fourth column. And then you get, so what is the answer, first of all? Wait, is it? Yeah, it's coming out to be 1. But I am expecting, no, so, right. Yeah, it's coming out to be 1. Right, that's fine. But it's coming out to be 1, but what does it mean combinatorially? See, so this one here means that there is a edge from 1 to 2, right? So yeah, this means that there is an edge from 1 to 2. And this 0 means that there is no edge from 2 to 4. Similarly, let's look at the last entry. This means that there's an edge from, or maybe that's not important. So let's see. This one means that there is an edge from 1 to 3. And this one, pay attention, this means that there is an edge from 3 to 4. And those are the things you are multiplying. Right? Exactly. Exactly. And those are the only kind of things which will contribute to a path in a square, right? Yeah. I mean, so any path of length 2, yeah, any path that you get of length 2 is gotten like this only, right? One edge to some intermediate thing and then back to the thing you want. And those are the things which you will get by this multiplication, right? So this will be like from 1 to I, and this you will multiply with I to 4. Right? And the product is 1 means that there is an edge from 1 to I and then from I to 4, which means from 1 to 4, there is a path of length 2. Yeah, and the number of times you get 1, that will be the number of paths from 1 to 4 of length 2, right? So this means that in a square, the ijth entry is equal to, and this is it's even there in the Olympiad combinatorics book. This is a regular lemma that is used in a lot of combinatorics problems. But also I had discussed matrix multiplication a little combinatorially once, but anyways, that's fine. That's why I gave this question. Okay, so this is, that is there, but that is not much in combinatorial. Like if you look at combinatorics and matrices kind of questions, then this is kind of thing is also used. Okay, or if you look at graph theory, like from graph handling, anyways, that's not important here. But yeah, Van der Waals matrix is certainly very, very important, right? So a square I comma j is number of paths from I to j of length 2. Okay, so what I've written is slightly incorrect because it's not really paths. It could, vertices could repeat, but there it's just 2 edges. So, a 2 to length 2. So it doesn't matter, but in general, you can understand. Yeah, you can repeat. Okay. Now, this is your homework that you try to use induction, right? To use induction and show that in a to the power n I comma j, this will be number of paths of length n from I to j. Yeah, and you can understand. You can just use induction. Yeah. So because you see, if you want a path from I to j of length n, or just I'll say a sequence of j edges, n edges that lead you to j, then it means that here you at some point you have n minus path of length n minus 1 to somewhere, and this will be the entry in a to the power n minus 1. I comma anything, I comma k, and then k to j, that edge will come. So you understand, right? So this analogous. Now use all this to complete the problem. Now it's not difficult. That some power will be 0. Okay. Try to use this to just have a look. To do this homework, but make sure you've understood this induction part. Okay. All right. Okay. So there are no questions then. Okay. Now, as a further challenge, what you can try is the following. Okay, let me not say the graph theory question because that's easy now. But what you can think of is in any matrix in which there are only zeros on the diagonal, okay? Zeros on the diagonal and below, okay? Then in the other places, it could be anything, in fact. And still this will hold. So this is actually not a graph theory. It can be done like this also. So, but this is not, may not be done by graph theory because I could put even some irrational numbers and so on. Then you have to think, maybe it's weighted. If you take weighted edges, something, yeah, you can think. It will say it's an interesting question. Okay. So either you can do it by graph theory or pure matrix theory. Okay, some induction you can use. I don't know, right? So this is a, and this may be actually easy to do because it's more cleaner statement, right? There are no details in that, computational details. It's a good question, okay? So there are zeros on the diagonal and below the diagonal, okay? And above the diagonal, it could be anything, and still the power, some power will be 0. And you can guess like fourth power definitely will vanish, maybe before that also. That is a interesting problem. Try. It's not very difficult. Huh. Which book? So the way I learned matrices was first I had done it from the basic books. Then I learned it from some JEE books. Like I remember the first time, maybe there was a book by G. Tewani, but it was not very, it wasn't Cengage. I remember the first time maybe I learned something good. So before that, obviously there are the ICC books, Saha and Saha in my days and so on were there. Then after this, formally, yeah. So this was not so bad because this made me ask some questions, okay? Because that time I had more time and so I was asked a lot of questions. And then, but after that, really, if I would have to tell you the truth, Artin, which I had said earlier also, Artin, there is a first chapter on matrices. Okay, and this is where I learned. And it's impossible, it's very difficult to learn these things, this inside view from this just the high school books. Artin is a college book, okay? Yeah. Mm. Huh. Yeah, it is totally mechanical. Yeah, yeah. So I'm telling you now. So I started to pick up matrices basically from Artin was a very good first impression. Okay, I did not. That is a very good book, but I have not read it. Yeah, but that's also a very good book. But also, I forgot when I was not very good at reading books, even now also, I used to watch these videos by Gilbert Strang, and very good memories of watching this. It's also very good. Okay, it is very elementary. If you look at the first few videos, it's again, it's like, so okay, but this was a another very good thing. And basically, because I was reading graph theory in high school a little bit, and you guys also would have seen a little bit. And there also, when you see this topic of adjacency matrix, then you play around with adjacency matrices, you learn a lot of things like these kind of things. This I saw when I was reading adjacency matrix. If I have to tell you the exact thing, from Brualdi. Brualdi is a very basic book, but I think it has a little bit of, in the graph section, you see adjacency matrix. If it doesn't have, then forgive me. But adjacency matrix I read from some book. I think it was this book. And there it kind of struck, oh, okay, so matrix multiplication has this nice, okay, a nice this thing. Okay? And obviously over the years, I've learned other things. Okay, so which I now can see in elementary ways. Okay, yeah. So Brualdi graph theory portion, and but Artin is wonderful. I can tell you Hoffman and Kunz also, but Hoffman and Kunz is not readable because initially he will do a lot of other things and then do. But Artin I had read a little bit like during my 12th, and yeah. Okay. So anything else I had read? Don't remember. And I used to just solve a lot of determinant questions, from those bad JE books. And in that, I gained some computational intuition. And that time I didn't have proofs of those things, like A transpose, B transpose is B A transpose. I mean, obviously one can prove it computationally, but I used to always try to wonder why this is true. Like, why is it really true? Obviously now I have a better answer. Yeah. So those computational things, why this is true? You mean to ask like fundamentally, like not computationally? Yeah, you can prove. Yeah, so it's not easy to answer. Yeah, I don't think I can answer now. Like I can tell, but it is a little, yeah. Basically, this A represents a very special function from a certain space to a certain space, and this A transpose also represents a special function. And when you understand that A transpose represents that kind of function, then you will, and similarly B transpose, then you will understand why it reverses. But understanding that space is complicated because that space is the space of functions from that space to some other space. It becomes, but that really gives a real meaning of this. Otherwise, I don't see. That is why. Yeah. So you have to look for it yourself. You have to look for it yourself, to ask people. Yeah, but you have to try to read, like you have to try to read from Wikipedia and get motivation, like, because see, the motivation of those books is just get the solve the MCQs, right? So you can't blame them. But like, see, when I discuss matrices with you, I hope a lot of things are now intuitively better understood. Right, like the matrix multiplication is a linear combination of rows, factorization of matrix. Those things I tried to tell you, right? And the multiplication is like, so every matrix represents a function. So multiplication is associative is now clear because this is composition of function and so on. So like some of things I gave, but to find more, you have to search, because otherwise you won't get. That's hard. Application like what? Yeah, so I mean, so this was exactly, this problem which I gave was exactly like that, right? So no. Yeah. Yes, so that also I had shown, right? So when you look at this linear system of equations, then to answer questions about that, we went to matrices, and you also do invertible matrices, unique solutions. No, like the question and the answer doesn't involve matrices. The final answer and the initial question doesn't involve matrices. But going okay, that's but that's okay. But you can just imagine, right? You have matrices, and you start with you have a system. No, you have a system of equations, then you build a matrix out of it, right? And when you do those row operations on this, basically when you simplify the simultaneous system equations to solve, you are basically, that is basically like multiplying the matrix with some special things, right? And then that connection, right? So So yes, that's a connection. And then there are details, but you can think, or if you are absent, then yeah. But I can share you some resource you can try to read or watch. Okay. So that's why I did that topic, because that is missing in high school, at least from the books I know, the English language books at least. It must be there in some other languages. But anyways, yeah, let's move on. Let's move on. So that's why I gave this question, because even in this question, essentially we are trying to prove that there are paths are not long enough. There are no long enough paths because this graph has no cycles, right? And so if there was a cycle, then there would be longer and longer paths, and then this power will not become zero. You see, and so that's the importance of this question. Okay. Yeah, that there are no directed cycle. Okay. Yeah, so let's come to the next question. So it's question number 4. That was precisely why I did those few classes on matrices to, back and forth. Yeah, let's go to the next question. So this question is actually also very interesting. I don't remember the exact, but I remember the context. So fix two letters A and B. So letters A and B, and L is a basically set of strings that we generate, from A and B. That can be generated, but there are some rules. Okay, so the rules are that you start with the empty string. So let's denote that by 1. So it makes sense to say that. Yeah, so we denote that by 1, and then if something is wait, so did I okay, if alpha is there in L, so let's write it. Okay, if alpha, that's right, if alpha is there in L, then that implies that A alpha B and B alpha A are also in L. So basically, with anything, you can append A and B towards the end, means either AB or BA in the end, then that is also in L. And second condition is if alpha and beta are in L, then alpha beta is also in L. If alpha and beta in L, that implies that alpha beta is also in L. That's, yeah, the condition. And so you see, it means that if you start with the empty string, then alpha can be the empty string, meaning just nothing. Then you can append A and B to the endpoints, and you get AB, and then you get BA. And you can get more terms, like when you have AB and BA, then you get ABBA. Okay, and in this way, maybe you can append A and B to the end of the AB and get AABB, and so on. You can get many terms. Okay, you can already see some kind of yeah. I have to do this in all possible. Okay, now determine all possible. Oh God, what did I do? Determine all possible strings that you can get in this way. Okay, so describe all the strings. Describe all the strings that you can get. Okay. So say something about what things can you get or what things you cannot get. At least something you should be able to say, right? What is the property of the strings that you are getting? They have some property, some common feature. Look at the rule. The rule will tell you. So what is a common feature? So someone, there is something, some common feature. You see, every time you're a reflexive nature, what do you mean by that? Hmm. It's just a symmetric. Symmetry. You're kind of saying that if L is there, if some string is there, then its reverse is also there. That you are saying, and that is certainly correct, right? Does everybody agree? I mean, both the rules preserve that, right? So that's already something you've said. That's the point, yeah. So try to say something. That's the whole point, yeah. So if alpha is in L, then reverse alpha is also in L. This is good, right? Already something. Now other people can also say some things. Some common feature. Yeah, because you can see that at each stage, that kind of symmetry is being preserved, right? That if alpha is there, right, then if you're putting A and B, then you're also putting B and A. If it's also preserved, see, because yeah. Okay. Chandan, do you see this also? Okay, so you see the way I'm saying is that basically in the rule, A and B are not distinguished in the rule, right? Any two strings that we are attaching are not distinguished. They can be, and also A and B are not distinguished, like symmetric statements. If you replace A and B, everything, the statements will not change. So, so this is clear. Sometimes they are palindromes, right? So what kind of palindromes are you going to get? What kind of palindromes can you not get? So since you have said, I'm asking a more specific question. What can you say? What kind of palindromes can you get and what you cannot get? Think. So palindrome is something that when you read from the left to right, or you read from right to left, it's the same thing. The exact thing is the same thing. So like 2002 is a palindrome. 2022 is not a palindrome. Yeah, reading from right and left. Okay, so you cannot get odd palindromes. So palindromes are even. Now the question is, can we get all even palindromes? So no. So symmetry doesn't mean that it has to be even odd, right? Think so. You cannot get any odd string at all. In fact, right? You cannot get any odd string. That also you can see. That should be clear, right? Every time you are increasing the length by 2, or you're taking 2 even length strings and you're doubling them, or you're attaching by induction on length, you can say, right, that it's always even. So all strings are even length. So there's nothing odd length here in this thing. Now my question is that this could be like a simpler question. Prove that you can get all even palindromes. So can you get all even palindromes? You're right. So if your palindrome starts with AB, it should end with BA. I agree. No, but you see, palindrome doesn't need to be like that, right? It could be like this also, and something in the middle, which is also palindrome. But think, you can get. Yes, certainly. Think. You can get. You can get 2 consecutive. So this is interesting. The answer here is yes. You can already feel. You can try to make the small ones. You see, you can make. Try to give an argument that you can get all even palindromes. Yeah, so that's the, so you don't show the details. I think that should be sufficient. So you guys try this, okay? Induction on length. Okay, but the point is you don't even have to do that, because a palindrome, just as my reasoning is that if you want to get a palindrome A, what is a palindrome like? It is like B and B reverse, right? But then that's clear, right? Because B, oh, no. So we have not yet proved that the B will be there. Yeah. Okay, no. So forget it. Leave it. Sorry. So you try to just do it by induction on length. Okay, that you can get all. So yeah, don't say this. This is easy. And so another feature which you can see, which is generalization of palindrome here, and you can see it from the pattern that always there will be an equal number of A's and B's, right? So L is a subset of strings with equal number of A's and B's. That's clear, right? You don't never get something which has unequal number of A's and B's. A, B, B, A, okay. No. You're right. No. So that's certainly that's correct. So I'm saying something wrong. No. That's right. This is certainly correct. Incorrect. Yeah. No. But no. So what? So okay. So maybe then. So I've said some wrong things. Then I think. Yeah. So can we get all palindromes? This is, I think, still a question. So can we get the, so as you've said, A, B, A. Can we get this palindrome? Yeah, Chandan, I think you are also saying something like this. Okay, how? A, B, B, A. Yeah, we have that. Yeah. But we cannot add A on both sides. No, because, so that you see, you add a and a B, or a B and a A. No, so Chandan, I think that's what you were saying, right? So that's the point. You're right. So you cannot get all palindromes. I'm sorry. As you can check that you cannot get that thing. Yeah. No, so the answer is no. Okay. But I mean, from here you see that what you get are the ones with equal number of A's and B's, right? So all strings in L. So that was a mistake. Yeah. Have equal number of A's and B's. So this I want you to say the, or someone, or you, if you have, on the details, because this is the main thing. No. So okay, not this particular thing. This particular thing is simple, but the converse of this, right? This is simple. Because you see, I mean, any small, you can, yeah. So you have a big string, it's made out of, so if you have any string A, it either comes out of attaching to some string. So there was some string B and you attached A and B in the end, or there was some string C and you attached, like B, C, and A. Okay, you either do this, or there was some B and C and you just multiplied them, right? So you see, by induction, if each of them have equal number of A's and B's, then what you make also has equal number of A's and B's. So that is simple. Yeah, but we want to show that all possible such things can be gotten. Show the converse. Yeah, I think it is true. Yes. That any string with equal number of A's and B's, you can get like this. So in A, B, B. Mm-hmm. Yeah. So A, B. Yeah. So now you try to make this and you see you'll be able to make this. And that will actually help you to prove that it is possible. It will make you sure. So you have to try to go against yourself and try this, and both ways you have to check. So can anyone produce this thing? This last yeah, right. So you take ABBA and add AB on both sides, or you can just take, or you can also take this and you can append. So this is the alpha, and you have also have AB. Yeah. Okay. So you can get this. This one we have to do. We should do this now because this is the main thing. This problem is very interesting because it shows that some very complicated languages, or rather not complicated, but something that is not described, it doesn't seem like it is described recursively, right? Equal number of A's and B's, it doesn't seem like it can be described recursively, right? But it can be. That is the, yeah. And this is just a simple induction question, but these are, what is the name? I forgot. Yeah, these are what are called, so these can be generated by some machines called push down automata or something. I forgot the name. Yeah, so, okay, I know the logical part. That's called context free grammar. Okay, that can be used to generate these. So this will be the next thing you study in combinatorics. If you study more combinatorics on words and things like that. But this is a elementary induction question. So try to use induction, try to assume that for length till length k, you can do it, and higher lengths, try to prove. So assume strings of less than 2. Okay, now you take a string of length 2n. So less than 2n means, less than equal to 2n minus 2. Now you want to show that this can be gotten. You can do some sort of casework. After the 2n minus 2 length, you want to add ABBA. Okay, so if you add ABBA, then what kind of strings of length 2n you will get? Those which start with A and end with B. Right? Sorry? No. But I'm saying that if you take a string of small length, right, of length 2n minus 2 and add AB in the end or BA in the end, then you'll get a string of length 2n, which will have equal number of A's and B's, and but it will start and end with different things. Okay, so those you can get by this, but that's not all, right? So that's what I was saying. So basically, I mean, I would have said, okay, so now I take the string of length 2n, equal number of A's and B's. What are the possibilities? It could either look like this, or it could look like this. And these two are done from what you're saying. But now you need to do just the only other case, basically A. How will you build this? How will you build this? Is the question, is this clear to everyone? Like, this is just natural casework. You could write it in other ways also. But now if something starts with an A and ends with an A, but it has an equal number of A's and B's. Right. Okay. That's right. That's not completely tragic, right? It can still be said. Yeah. So you're right. So if there are like k, if there are, I don't know what I should say. So yeah. So if there are 2k B's, then there are 2k plus 2 A's, right? Something like this. Yeah. No, sorry. So it should be opposite. It should be opposite. Sorry, you're right. You're right. Yeah. This is the number of A's and this is the number of B's. Yeah. So this means that this will not come by the first move of appending A's and B's. Obviously, will not. You have to do something else. Yeah. So this has more B's in the middle. Okay. But you have to think. This kind of ideas you guys would have seen if you have done maybe. It's used in many places, but it doesn't mean anything. You can do this just from here. So you can take a small example, right? You can take some example and try, right? So you have A, and we already have, but let's take a more complicated example. Let's say there is another A, and then there is B, and B, or let's say B, A, B. 4. Yeah, this is right. So how will you get this kind of thing from smaller strings? Appending. Yeah. And you see, the place where you're appending is really the place where things equalize. Absolutely. Yeah, right. You want? So equal. And then obviously that implies this side will also be equal. I mean, that's, you have to just care about the left. So you have to scan from left to right, and you will have to prove that at some point the number of A's and B's become equal. Because they eventually become equal. Okay. And initially the number of A's is more than number of B's. So I mean, at some point they would have become equal, right? Think like, I mean, if there is a B, then there's nothing to do. But if there's an A, fine, increase by 2. But I mean, at some point the B's have to catch up, right? Because there are more B's here. So it should be clear that at some point it will be equal. It's like some sort of a discrete intermediate value theorem. right? The number of A's is more than, like, the difference is more, but then when you come here, the number of B's is more. So at some point, the difference should be 0. That way, or you can say in any way that they become equal. You can do by any way. Okay, that's up to you. So then we are done. Okay, and this kind of thing is used in many places. Like I feel when we do Catalan numbers recursion, there also we use, like, we break the equal number of zeros and one. How many strings are there like that? In which A's always win, and so if A are in the middle or something, or at least, and then we break it where it becomes equal in the middle, and we do recursion, because this part, that part, both should be like Catalan sequence, subsequence. But anyways, this is, but I don't, that part is not important. But is this clear? Yeah. Okay. Is it any questions? No. If there are no questions, then I'll move. So I mean, you can see that the questions are not difficult. They're just a little they're just a little different type. And yeah, this is fine. This is not difficult. It's not a. Is it a very difficult question? Do you feel it's unfair question? No, right? I don't feel it's unfair. It's a little difficult during the exam, but it's kind of, it's not unfair. Like maybe they can ask you an easier version. Okay. And also the previous question that we did, what was that? That was also a little, yeah, but yeah, that was a little tricky. But anyways, the first two were easier. Some questions are hard. Fifth one, let's see. Fifth one is, sorry. Aha. But if you take enough examples, yeah, but okay. Yeah, maybe I can, yeah. Yeah, that's the main thing. So if you take a lot of examples, and this is the key thing I've seen, if people don't take enough examples or small cases and try to see patterns, a lot of these questions are done just by that. And a lot of people whom I have met, and some of them are like some of those who like don't prepare much and they still qualify. Okay, I know a lot of people, like they were just, they'll say, I'm just preparing for JEE Advanced, and they just, someone, my friend was writing, so I also wrote, and I cleared, I came here, whatever, right? They say like this. Okay, so the thing I've seen with those people is that they're very, when they see a problem, they are not like me, not lazy. They are extremely, energetic, in the sense that they'll pounce upon it, in the sense that they will just try a lot of things, in the sense of lot of patterns. They'll try quickly, they'll write the first 10. Okay, and some of us are try to apply some theorem, some noble, we know a lot of, some of us know a lot of theory, and we try to, but that's fine. But attack the problem with a lot of energy, in the sense of small cases, try till 5 6 cases, and you will see something. And then most of it can be proved by induction or some things. That was the thing. I mean, if even in the matrix question, I'm sure if you guys didn't do it, but I've seen this in lower batches, they do a lot. They just energetically find a lot of things, and they quickly compute and tell me. Okay, even though maybe they cannot spot the pattern because they're a lower grades. But this is the thing, is you guys are lacking a little bit. Okay, what I was expecting, if even it's an exam, even if you don't know anything, right, you can just square the matrix and see what is happening, right? If you square the matrix, you would just see that the number of zeros is increasing, and maybe you find something. But you should do that. Okay, maybe the question was incomplete a little bit, but that's what I want. Okay, how much you write, like, so if in a 2-hour exam you should write more. Okay, just try these questions, you can try a lot. So at least in this string question, you guys would have tried a lot. Okay, so that is the energy I want. And in question number 6, everybody just wrote that he can get 44, but nobody tried to get the other even numbers. Maybe at least forget 44. You could have tried to get 2, 4, 6, 8, 10. Nobody did that, right? Maybe you did it in your rough, I don't know. But yeah, if you write that, then at least you will know. So if energy, be more energetic in that sense. Okay, question 7, maybe, I don't know, it's a little, it's easy, but it's maybe not too much to try. Yeah, so anyways, let's see. Okay, and all these questions are unique. That's the good thing about writing this mock, because these are all just made out of, because you won't find this in any in any previous context. I can guarantee you that. Okay. Yeah. So these are maybe not nothing. There's nothing original anywhere, but the point is these are unique. Yeah. Yes. Original meaning that these results are already can be proved by mathematicians. Okay, so this question is GCD of x, y, z is 1. So there are 3 numbers in which the GCD is 1. Okay, this is also a very interesting question. 3 numbers with GCD 1. Okay. Okay, so maybe I had A, B, C there. Anyways, yeah. Anyway, so numbers. Now I want to say that there exist A and B. Okay, such that A is congruent to, or rather, same thing, but x is congruent to A mod z. So you want to take something like A, and y is congruent to a B mod z. So take something which is leaving the same remainder as y and then divided by z, such that A and B become coprime. Okay. This is another gem. And this was a lemma which not me, but someone needed to prove some very hard, not some difficult result. And they were just discussing this with me. So I was like, okay, this is just and the solution is completely simple, elementary. Seems like you don't even need any theorem, no, not even Bezout's theorem, anything. So again, I mean, this is just, you can't just think like this, right? So you have to take some examples. So yeah, let's say that you take some, yeah. So what examples did you guys take? Tell me something, tell me some examples you want to take. 2, 3, 4, no, so don't take, don't take that all 3 are like actually coprime, like pairwise coprime, because if you take that example, then you won't learn. 2, 3, yeah, okay, sorry, yeah, sorry. Sorry, yeah. So that's right, yeah. So you take 2, 3, 4, right? The city is 1. So then, yeah. So then, how do you get the A and the B? But here in this case, it's a 2. Yeah, that's why I said. But yeah, I guess we can. I can just say 2, 4, and 3. Yeah. Okay. So how would you shift the 2 by a multiple of 3, or 4 by a multiple of 3, or both, to make it coprime? Yeah. So it's very simple, because I mean you just take 2 plus 3, right? I mean this is your A. So if you just, it's a shifting question, right? If you shift the A, shift the 2 by a multiple of 3. But in this case, we just shift it, and we don't need to shift the B. Okay. And these two become coprime. Is it now making sense what the question is asking? It's not like a modular arithmetic, some, language question which requires some theorem. It's just like this. You can shift the x and the y by a multiple of z, so that they become coprime. So tell me some bigger numbers so that it becomes more interesting. No, 1 minute. So let me not take that, because no. So this is not good, because I want that none of them are pairwise coprime. So you should take an example which is more on the edge, right? So I will not. So I'll take something different. So maybe we can take 60. 12, yeah, but 12 becomes a divisor, which is again, but you can take 12. I was thinking 12, but 60. So these two are not coprime, and so then what should I take as the last one, so that all 3 become coprime? All 3 together become coprime. But no, but I want, yeah, 33 is not going to work. Yeah. So 3. No. So the problem is that this is not a good example. That's why it is not working. Maybe. No. You're right. So 5, 3. No. This is not a good example because the 36 doesn't have enough primes, right? We just want to make that two of them are not co-prime. So maybe you can say 7 into 2 into 3, 6, 7 is 42, right? And then I can take 35, right? Okay, yeah, this is good, right? So yeah. Try it for this now. Okay. Yeah, Adish, are you there following? I mean, we're trying to take example. Okay, he's not here. Okay, all right. That's the thing. Okay, no problem. Let's. So now, if you just try to shift the A or the B by a multiple of C so that they become co-prime. You have to offset. So this is the X and this is the Y. How can you offset the X or the Y so that they become co-prime? Offset by a multiple of 35. Yeah, right. It just seems to work like that, right? So you just add a 35. Does it work? Yeah, right. These two become co-prime. Right. So now what would you want to do from here? Hmm. Yeah, x plus 2z, x plus 3z. Mhm. That's right. Okay, that's right. Ah, that's the thing. So you're coming down to something more specific. You see, that is the problem solving thing. Chandan, do you see? Right? Because this seems too random, and also it seems like it's not necessary. Or I don't know. We cannot explain how someone comes with that, but that seems like the right thing to do. You see in the examples also, we have to only also it feels like that, right? The GCD, I mean, you could subtract the NZ and something. So that's the point. So point is we want to fix the Y and now we want to do. Okay? So if X and Y were co-prime, then you can just take M to be 0. Then there's nothing to do. So think. So we are getting closer. So I'll remove this. Okay, let's keep the sequence. Maybe some sort of PHP can come in. I don't know. But I don't think this will be a PHP kind of question because it seems very existential. It seems very constructed, not existential. You can actually construct them. So you want x plus mz and y to have no factors in common. So you want to, any factor, you want to take a m so that it kind of kills that factor in the summation. Or you can try with contradiction, maybe. Yeah, so you can try to use the, yeah, in fact that was one of the ways I think in which the other person had told me, but I did completely differently. So yeah, so you how do you use that then? So you want to show that there exists maybe not a and b but p and no t and s such that plus ys is 1. You can uh-huh, right. So we already have this. That is the thing. Yeah. Can you? Yes, it does apply for 3. That's a very interesting. It applies for all numbers. Yeah. 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 Right. So this thing, how do you get this? So it's all about now. It's all about maybe smartly breaking the T3. That could do the job. I don't know. How would you want to break the T3? Yeah, that's right. That's right. So, but then there is something which is a little bothersome, right? Because you want to break the T3, not just break, but it's like it would be good if the T3 was a multiple of T1, right? But that is, yeah, but that is not happening. But otherwise, if you just break, so if you just write T3, write T3 as Z Q plus, no, ZT, no, T1, T1 Q plus R, yeah, then you will get this, and then plus zq times t1 yt2, and then there will be zr. But this does not, this what I have done doesn't look very useful, because see the m has to be described, or yeah, but that's how would you know if m has to be described or just shown to exist? So, I mean, that I'm not able to make use of that. So what you guys can think of is directly trying to look at, prime factor. Like, just imagine, I mean, if P divides Y, then, I mean, P X plus MZ, what would you have to do to make sure that P does not divide X plus MZ? See, that's what you have to do, right? If P divides Y, you want to show that P does not divide X plus MZ. That's the kind of M you have to make. Yeah, that P does not divide the sum of these two numbers. Okay, now just you can imagine that this basically has two cases, right? One case is P divides X and the other case is P does not divide X. So you try to at least do one of the cases. How would you avoid that prime? So let's say that P divides Y and P divides X. How would you make sure that P doesn't divide X plus MZ? What kind of M would you need? So remember that this implies that P does not divide Z because X, Y, Z are co-prime. Now, how would you ensure that P does not divide X plus MZ? Exactly, right? So you just make the M. So in M, you don't put the prime P, okay? So you make sure that the M is co-prime to P, or simply you don't put the prime P in M. So you know what not to put in M. Okay, now this is your homework. Think about the other case and see what you have to put in M. Now you have to put something in M to make sure that the sum is not divisible by P. And then your problem will be done. It is just very simple to think. But I've given you the hint, don't want to complete it. Just think. Something like this you have to do so that you know what to put in M. So it's very simple actually in that way. But no, but fine. I mean, you have to, yeah, this was not easy for me to come up with. This one, there are a lot of examples and every time I'm seeing that only shifting one number is enough. But I'm not able to prove that because obviously I don't know I've not proved the statement, so how would I know? And even, I'm not able to reduce it to that. But still, let's say we try to do it. And yeah, so I tried this problem on 3 days, 3 different days, like maybe 5-10 minutes. Yeah. When I am just, on the way or something, sitting, just eating food, thinking. Then I got today morning I came from the library and then say, let me try this. I suddenly start. Yeah. Because when I made this question, I couldn't do it, but I knew I could do it, or I knew I could ask someone because they had given me the problem while discussing. So, yeah. Okay, so let us stop here, okay, because we're not able to complete this as usual. But you guys have got some hint for the questions which you couldn't do. You can complete it, and also you have done some questions. Now for 6, as I've told you, try to get a way to work with the numbers on the board so that you get the number 2, 4, 6, and then you will know how to get 44 because you guys are smart enough. Once you can know how to get 2, 4, and 6, you will see, okay, something is working. Okay. And in problem 7, we'll have to see, okay, some sort of a monovariant. Okay, try to increase the number of maybe positive things in the matrix by multiplying. Find a B and C so that things become more and more positive in the matrix A. So remember, B and C is up to you, and you won't get it in one shot. You have to first do a B1, C1 so that some improvement happens. Then you again multiply by B2, BC2, another improvement happens, and something, something like that. Okay. 8 is also not difficult, but you think about all these two, then you can see. 8 is, you will see, it's just very, that's just induction actually. Okay. It's like, yeah, I mean, yeah, let's see. So we'll see it next time. Okay. All right. So that's it for today. We will meet next on Tuesday, hopefully, and then we can continue. And sorry for the mess of yesterday.